Last time we were working in section 1.3, talking about evaluating limits analytically. We're going to just run through real quick a few of the things that we had last time because we're going to be using them again. Some basic limits we had here were that the limit of a constant is a constant. The limit of x is actually evaluating the value at x. So the limit as x approaches c of x is c, and then x to the n is c to the n. We had a scalar multiple that says that you can actually multiply the scalar after you find the limit. If you're doing a sum or a difference, you can do the sum or the difference of the limits. Product, you do the product of the limits. The quotient is the quotient of the limits, and the power is the power of the limit. It's all these wonderful features that we're able to use. And then we had some of those sort of compiled all together that gave us the properties for polynomial and rational functions. So if it's a polynomial, again, you can evaluate it at the value that you're looking at. You can actually plug the number in, so to speak. And for a rational function, you can at least attempt to plug in the number, and that works just great unless you end up 0 in the denominator, and then you have to look at some other features and see if there's any way to simplify what you have. And then we had one more, and it was radicals, and it said if we had a radical that we could actually take the radical of the limit when we're done. And that's in some sense a property related to the power one that we did before. Okay, we had seen this example right here, example number 3. We talked about a few things just to remind you. We write limit on every single step until we actually plug the number in. Okay? Just because it looks like a rational function like on 3 and 4 doesn't necessarily mean that you always have to factor, so don't get carried away. The goal is to simply plug the number in. So if you can plug the number in at the beginning without factoring, then you've saved yourself the factoring, right? So make sure that you have to factor before you factor. So taking a look at this particular problem, our goal is to try to plug in the number that we're given. So this is x approaches 4. So if you were to plug in the number 4, what will you get on the top? What will you get on the bottom? So try plugging in the number 4 and see what happens. Okay, so you're saying that you get 0 over 0 if you try to plug the numbers in. Does that look right? Okay. When you get 0 over 0, that's sort of a magic clue, if you will, that tells you that you are going to be able to factor this. Okay, and the 0 over 0 is giving you that clue that there's something that's going to factor out. It still may have a 0 in the denominator when you're done. You don't know, but at the very least, you're going to be able to factor and reduce this. So we're going to take a look at factoring and reducing this. So this is the limit as x approaches 4. And we're going to attempt, anyway, to factor the numerator and to factor the denominator. All right, so the numerator is x squared minus 5x plus 4. So how will that factor? So if you'll remember, when we do factoring, we need the first terms that we put inside of our parentheses to multiply to give us x squared. So that's x and x. We don't have any choices on that. The last piece, the constant term here, tells us what we need to have in our last two terms to be multiplied together to be. So we either need 4 and 1, because 4 times 1 is 4, or we need 2 and 2. I mean, those are our choices, okay? How do we decide which one's the one we need? The middle term, right. We need it to add up to 5 in the middle. So it would be 4 and 1. And the other thing is that we have to decide on our signs. Because our 4 at the end is a positive, it means my signs need to either both be positive or both be negative. That's how I get two numbers to multiply to give me a positive number, right? Both positive or both negative. Which one do I need here?
Both negative.
I need them to be both negative because my middle term is supposed to be a subtraction of 5x, right? Or minus 5x or negative 5x. So this is what we have on this one. How about number 4? How about the bottom of this one with the 4 plugged in? We still get a 0 over there. So we're going to factor this. I'll start with it. It's still going to be, whoops. Pen's a little bit smaller than I wanted, but now it's too large. Let's try that. That's all right. All right, so I've got x on both of those. I have an 8 at the end. So what are my choices for things that multiply to give me 8?
2, 8,
4 and 2. And 8 and 1. And because this is a negative, what is that telling me? Yeah, I need one of each. One sign needs to be positive and the other one needs to be negative. So since the signs are different, what we actually want is we want to figure out which one of these differences gives me 2 in the middle, because one's positive and one's negative. So if I take 8 and 1 and I take their difference, I either get a positive or a negative 7. If I take 4 and 2, I either get a positive or a negative 2. So it's the 4 and the 2 that I want, right? Yeah. And do I get a positive 2 or a negative 2 in the middle? What am I supposed to have? Negative. So that means my 4 needs to be negative in order to give me a negative 2 when I add them together. So this is 4, and then this one's 2. All right, so is there something that will factor out then? Cancel out. Yeah, the x minus 4, right? So as I cancel that one out, what I notice then is that this gets rewritten. And it gets rewritten, okay, come on, with the limit, because I haven't plugged the limit value x equal 4 in yet. So this is the limit as x approaches 4. The numerator is now x minus 1, and the denominator is x plus 2. Now that we've cleaned it up and simplified it, we attempt to do what we did at the very beginning again. That is, plug the number in. But this time it actually works. I can put in 4 minus 1 and 4 plus 2. So what do I get on the top?
3.
And on the bottom?
6.
And does that reduce?
Yes.
Yes. So the limit is 1/2. Every step is equal to the next one. If there's an x still in the problem, there's a limit still in the problem. Once the x is evaluated at 4, the limit notation goes away. They go hand in hand. Okay? Any questions on that one? Because the next one is a change of direction a little. Okay. Now, if I were to try to do on this one what I've done on the other ones, and I should, I still should, even though there's radicals involved, what's going to happen when I put a 0 into the numerator and I put a 0 into the denominator here?
0 over 0.
Yeah. So I still try to do this. I don't want to do more work than I have to, so don't start factoring or reducing or simplifying things if you could simply plug the number in, okay? So this one, though, I can't because I've got 0 over 0, and that's not a defined value. So what do? Well, somewhere along the way, in a trig class, in a pre-calc class, and maybe even an algebra class, somebody told you something about rationalizing denominators. Does that phrase sound familiar? What it usually meant, or what it did mean when you did it, is that you want to know radicals involved in the denominator. Okay? Well, what we're going to do on this problem is we're going to rationalize the numerator. So we're going to get the radicals out of the numerator. Because you see, the problem is that right now we can't clean anything up because part of the value underneath the radical is the x. It's a variable. I don't want the variable underneath the radical because I can't simplify anything if it's still underneath the radical. Does that make sense? So we're going to rationalize the numerator. Now, when you rationalized the denominator, what you did is you used the fact that differences of squares, so this is actually the fact that you used, is that when you do a minus b times a plus b, you get a squared minus b squared. That is, you don't get any middle terms. This is what rationalize the denominator is using. Yeah. Yeah, that's fine. Okay, so on this one, we're going to do the square root of the 2 plus x. And we're going to do the square root of the 2. But our goal when we multiply these is to get rid of the radicals. That is, I'd love to get rid of the square root on the first part and the square root on the second part. So the way that I do that is I use what's called the conjugate. That's the name of it. It's called the conjugate. But what it does is it uses the difference of squares formula. So if I multiply the numerator by it, I'm going to have to multiply the denominator by it. So I don't get rid of the radicals completely. I kind of move them. But that's okay. It's not a problem. All right, so what does this end up doing? So this is just the step that's telling me that I'm multiplying. I'm still going to have a limit when I'm done here because I'm not ready to evaluate just yet. And the whole point in doing this was that when I multiply this first numerator by the numerator I'm multiplying now, I only have to multiply the first terms together and the last terms together because they are identical except for the sign between them. So if I multiply the first terms together, what is the square root of x plus 2 times the square root of x plus 2? X plus 2 or 2 plus x, because I just told it backwards of what I've written it. But yeah, I get 2 plus x. When you multiply something by itself and they're both square rooted, you get rid of the square roots. Now the sign will still be the same because this is a negative and this is a positive, so I'm still going to get the same negative sign that I had before originally. And then I'm going to multiply the last terms together. That is the square root of 2 times the square root of 2. And what do I get? 2. Now, please do not get creative or overzealous in the denominator and actually multiply that out. That would not be a helpful step. Leave it in factored form, okay? In parentheses, the whole bit. What do you notice now is going to happen in the numerator? Two plus x minus 2. Yeah, I'm just going to end up with x. The 2's add to 0, right? And I've got an x in the numerator and an x in the denominator now as well. So what's going to happen to those guys? They cancel to 1, right? So be careful they don't cancel to 0 or anything, but they cancel to 1. So again, I'm still going to write the limit notation, but we're getting close to being able to plug it in, okay? What's in the numerator? 1. And the denominator is the radical part that I multiplied by, the conjugate, from the first step that I did. Now, you might look at this and think, seriously, does not look any better than it started with, at least not much. I mean, really, it doesn't really look any better. However, I am able to plug in the value of 0 now without getting a 0 on top and a 0 on bottom. And that's the goal. The goal is not to make it look better. The goal is to be able to evaluate it. So if I plug in 0 on top and 0 on bottom, or 0 for x, as the case may be, I get 1 over the square root of 2 plus the square root of 2. Right? So that's the calculus part that we've done. All the limit stuff we've done so far is the calculus part. What we're left with now is actually simplification of either algebra, or you probably saw it more used in trig, okay, or a pre-calc course. So I've got 1 over, what is square root of 2 plus square root of 2? 2 square root of 2. Now, we do not want to have that square root of 2 in the denominator. That's the rationalizing stuff that happened, you know, when you learned some about trigonometry. So what do I have to do to get the square root of 2 out of the denominator? Yeah, I multiply by it. So I've got a square root of 2 in the numerator now again. Now all of this is multiplied together in the denominator, but that means that I've got the 2 at the beginning, and then what's square root of 2 times square root of 2? 2. So I actually have a 4. So this is the square root of 2 over 4. Every step is equal to the next. There's equal signs between all my work. As soon as the limit went away was when we plugged in the value of x, all of that. Okay? Any questions on that one? So when you see radicals, it's all about conjugates. Okay? The conjugate, when you've got addition and subtraction, looks like difference of squares. When we see the radical in the denominator on the very last steps down here, I don't have any difference of squares because there's no addition or subtraction. That's why it's simpler to work with when there's a simple square root 2 in the denominator. All right, we're going to talk a little bit next about trig, what to do with some trig evaluations, limits. So the limits of trigonometric functions, let C be a real number in the domain of the given trigonometric function. All 4 of these tell you that the limit as x approaches C of the trig function means you can plug the C value into the trig function for x. Now, of course, the catch is that it has to be in the domain of the given function. So sine and cosine are fantastic because they just have this wave pattern. Their domain is everything, so there's no problems. But all 4 of the other trig functions do have asymptotes, right? Think about if you remember the graphs of tangent and cotangent, secant and cosecant. So you can't just plug things in all the time. It really does have to be in the domain. But as long as you're in the domain, you're good to evaluate for your limit. used C because your book used C, but it looks kind of funny because, of course, secant, cosecant all end in C when you write the small, the shortened form down, so it looks a little bit funny. So if you don't like C, I've used other resources that use A. I think A is actually a little bit better on this particular one if you use the limit as x approaches A. All right, does everybody have those jotted down? We're pretty close. There are two special trig functions that we need to be aware of, and that's our next piece. Just take a look for the first one. Write the first one, actually write them both down for me, and then we're going to talk about them. So the first one says the limit as x approaches 0 of sine of x over x is 1. And then the limit as x approaches 0 of 1 minus cosine of x over x is equal to 0. So just look at the first one. What would happen if you plugged 0 into that function? If you plugged 0 into sine of 0 and you made it sine of 0 over 0, what's the sine of 0? It's the sine of 0. It's 0. Okay? So you'd actually end up getting 0 over 0 if you tried to actually physically just force 0 into x in this case, right? And the same kind of thing will happen on number 2. If you plug 0 in for cosine, the cosine of 0 is 1, and then 1 minus 1 on top is going to give me 0 over the 0 in the denominator. I'm going to get another 0 over 0. Okay? Looking at why these two special trig functions have these limits is actually not a Calc 1 concept. It's something that we look at in Calc 2, just so that you know. But we're going to take these as face value, that these are the limits. Now, actually evaluating them sort of from a numerical standpoint, you should have done that on your quiz today. That very first one was from your quiz today, and you should have done it with tables, because that's what numerical means. So if you look at tables, or if you actually looked at this one on a graph, that's not from your quiz, but if you looked at it on the graph, you would see the value approaching 1 as x approaches 0. The y value is 1. And the same thing will happen on the second one if you look from a numerical or graphical standpoint. Okay? So we're going to use these, I guess there was 8 of them, new features, new limit properties that we have, to do 4 more problems. All right, so again, the goal is to plug in the number, so don't get carried away. Don't start using things that you don't need to use if you don't need to use them, okay? Attempt to plug in the value. If I plug in, that is to say on number 6, it says the limit as x approaches 2 of sine of pi x over 2. Let's just attempt to plug in the value, okay? So our goal is to say that this is going to equal the sine of pi times 2 over 2. That's a terrible pi. Let's try that again. It's only slightly better. All right, so what happens when I have pi times 2 over 2? The 2's are going to reduce, so this is going to leave me with the sine of pi. And what is the sine of pi value? It's 0. Now would be a good time to make mention of the fact that if you're a little rusty on your unit circle values, I would suggest going ahead, just if you Google images of the unit circle, it'll pull up a whole bunch of them. Just print one of those out and keep it with you in your notebook. You know, work on memorizing them again, because they're going to come in handy quite frequently. All right? So go ahead and, you know, commit those to memory once again. Print them out until you have them committed to memory. All right, so is this okay? Can I have a 0 as my answer? Sure I can. No problem. The problem comes in when I have 0 over 0, right? And I don't have that here, so I'm done. I used the first of the trig limit properties that says I can simply plug the number in as long as it's in the domain and it works. Okay? How about the second one? Well, we'll attempt to do the same thing. The cosine of 5 pi over 6. Now, that one's probably not quite as strong in your memory as sine of pi, but does anybody remember the cosine of 5 pi over 6? Negative radical 3 over 2. And just so that we can say that I've reminded you sufficiently, let me show you something that I think of when I work on these. Okay, so on the unit circle, hang on. 5 pi over 6 is in which quadrant? The second, right? So it's over here, and it's the one that's the closest to the bottom. It's way down here. It's very low. And so you're over here. So the first thing to recognize is cosine, we're working with cosine. Is cosine positive or negative in this quadrant? And it's negative. Remember, cosine is the x value that you get at that location. Okay, so it's a negative cosine value. The next thing to remember is if you know the unit circle's first quadrant, you know the entire unit circle. It's a fantastic, beautiful, symmetric kind of thing. So this one right here, this one here, and this one here are really the only values you need to know. And that's it. As long as you know those 3 locations, I guess you could say, and the axes themselves, but those are not hard to remember for people usually. So as long as you know the ordered pairs, basically, in these 5 locations, you're good to go. Okay, so if you take a look, the one that I would be remembering would be this one right here, because this one is the mirror image when I flip it over into quadrant 2. All right? If you're looking at this one and this one, they also have wonderful symmetries, because x is one value and y is the other, and then you switch them. So for example, on the lower one down here, I have an ordered pair, x, y, that is that location. That ordered pair has a square root 3 over 2 and a 1/2. So if you think about it from that location, is the x value larger or is the y value larger at that ordered pair location? The x. I'm further away from the y-axis than I am away from the x-axis. I'm further to the left than I am up. Okay? So it's the x value that's bigger. Well, the x value bigger means that that's the square root of 3 over 2. Hang on, I think I need to write this a little bit larger. It's just mushing it all together at this point. And then the y value would be the other half of that. It's 1/2. So if I know this particular point, I actually get this one almost for free because I just have to reverse it. So this one's 1/2 square root of 3 over 2. So when I'm looking at this location right here, it's the same thing as looking at this location right here. I just need to make sure my signs are correct. The x value is negative when I'm in quadrant 2, so my cosine value is negative. And cosine is the x value, so it is the square root of 3 over 2. Okay, so some remembrances there. All right, so we're done because that's definitely not 0 over 0, right? Okay, let's take another one. Find the limit if it exists. Same directions as before. We have sine x over 5x. Okay, so let's try. What happens on this one if I plug in 0 for x? 0 over 0. So we can't just plug in 0 on this one, right? But this almost looks like one of the trig functions, the special ones. Which one does it look like? Sine x over x. Now, I want to show you this. I wouldn't expect you to actually write out all the details I'm going to show you, but I do want you to see what's happening or why what I'm going to show you is happening. This is the same as writing 1/5 times the sine of x over x. Do you agree? Sure. And then we had a limit property earlier in this actual section that says that when I have a constant multiplier, I can pull it to the front. So this is 1/5 of the limit as x approaches 0 of sine of x over x. Right? So the 1/5 is part of the solution as a constant multiplier. And the sine x over x limit as x approaches 0 is 1. So the answer here is 1/5. So then maybe is the question of what would I expect to see? This part. That's what I would expect to see. The 1/5 pulled in front, and the fact that you now have the exact expression that's the special trig limit. Sine of x over x as x approaches 0. Notice that x approaches 0 is not x approaches anything. It's x approaches 0. Okay? So if we were doing the limit of sine of x over x as x approaches 5, well, we'd just plug 5 in. We wouldn't have any problems, okay? It's only as x approaches 0. Number 9. Taking a look at that one. What happens when I plug 0 into that one? I get 0 over 0. The cosine of 0 is 0. The tangent of 0 is actually also 0. and then I have 0 in the denominator. I've got zeros everywhere. It's all not good, right? Any ideas about what we might want to do to simplify this, though? Identities from Trig. Now, if you go out to our Moodle Room site, I do actually have a list of identities. You're welcome to print those out and hang on to those. We're not going to get into the more detailed ones. Like, we're not going to probably need any double angle identities or half angle identities in this class, okay? But reciprocal identities, quotient identities, things like that come in handy. So in particular on this one, what identity might be helpful from what you can remember about your trig identities? Okay, I think probably the tangent one is the one I'm hearing people say, right? So what is tangent? It is sine x over cosine x. And as with working with identities back in trigonometry, sometimes you don't get the right one when you first try it, right? So if you had tried something else here and it didn't work, then you'd be like, okay, well, that's not the one I need. Let me try something different. This one is the one that will work here, because then I've got cosine x right here, one in the numerator and one in the denominator of the whole numerator, obviously. And this changes the expression into the limit as x approaches 0 of sine of x over x, which equals 1, because that's one of our special trig identities, our special trig limits. Okay, any questions on those? All right.